Today we are going to learn about visualizing gradient descent for better understanding. We will explore techniques to visualize gradient descent processes, including creating plots that reveal convergence patterns and optimization paths. Skills such as plotting cost function landscapes and interpreting gradient vectors will be taught. Welcome to our educational journey on visualizing gradient descent for better understanding. In this session, we'll delve into how visualizations play a crucial role in interpreting model behaviors and debugging training issues. We'll cover various techniques to visualize the gradient descent process, including plotting cost function landscapes and visualizing learning rate effects. Additionally, we'll discuss how to track convergence with loss plots and the use of 3D plots for multidimensional data. By the end of this video, you'll be equipped with practical skills to create insightful visualizations using Python.
Visualizing gradient descent is crucial for enhancing our understanding of optimization processes. It provides a graphical interpretation that can reveal whether our models are learning effectively and efficiently. By visualizing, we can identify training issues early on, such as vanishing gradients or divergence, which might not be apparent through numerical data alone. Moreover, visualizations facilitate the interpretation of model behavior, allowing us to understand how different parameters, like the learning rate, affect convergence. This understanding improves our debugging capabilities, enabling swift identification and rectification of issues. Visualizations also support decision-making during model training, guiding us in selecting appropriate hyperparameters, optimizing architecture, and ultimately ensuring robust model performance. Plotting cost function landscapes is an effective way to visualize the optimization path taken by gradient descent. These plots provide a visual representation of the error surface that the algorithm navigates. By creating contour and surface plots, we can better understand the shapes of cost functions and how they influence the model's learning path. Tools like Matplotlib and Seaborn can be employed to create these visualizations. Through these plots, we can analyze convergence patterns, identify local minima, and detect potential divergence issues. This insight is invaluable for tweaking model parameters and ensuring a smooth optimization process. The learning rate is a pivotal hyperparameter in the gradient descent algorithm, dictating the size of each step taken towards the minimum of a cost function. Visualizing learning rate effects can unveil how different rates impact convergence. By plotting the learning process over time, we can observe whether a high learning rate causes overshooting or if a low rate results in slow convergence. Visual tools can assist in identifying the optimal learning rate, balancing the trade-off between speed and accuracy. Additionally, these visualizations help in understanding phenomena like underfitting and overfitting, guiding us to adjust learning rates for enhanced model performance.
Loss plots are essential for tracking convergence during the gradient descent process. By plotting the loss function over iterations, we can visually monitor how well the model is learning. These plots serve as visual indicators of convergence, showing whether the loss decreases steadily, indicating successful learning. They also help in detecting overfitting or underfitting, allowing us to make necessary adjustments. The importance of loss plots in training cannot be overstated, as they provide immediate feedback on the model's performance. Tools like Matplotlib offer functionalities to create effective loss plots, enhancing our ability to interpret training progress. In the realm of machine learning, data often exists in multiple dimensions. Using 3D plots can simplify the visualization of high-dimensional data, allowing us to interpret complex optimization paths more intuitively. By representing cost function landscapes in 3 dimensions, we gain a clearer understanding of how the algorithm navigates the error surface. Tools like Matplotlib's Plot3D toolkit enable the creation of these visualizations. 3D plots are particularly useful in real-world scenarios where understanding the interaction between multiple variables is crucial. Whether exploring multidimensional parameter spaces or visualizing optimization trajectories, these plots provide invaluable insights. Gradient vectors play a vital role in optimization, guiding the direction in which the algorithm should proceed to minimize the cost function. Visualizing these vectors can provide insights into the direction and magnitude of the steps taken during optimization. By analyzing vector fields, we can understand the influence of gradients on the learning process. Tools like quiver plots and Matplotlib allow for effective visualization of gradient vectors. This understanding is crucial for model tuning, as it helps in adjusting parameters to ensure optimal convergence paths. Visualizing gradient vectors can also aid in identifying issues like saddle points, which can hinder progress. Python offers a plethora of libraries for creating powerful visualizations that enhance the interpretability of gradient descent processes. Popular libraries such as Matplotlib, Seaborn, and Plotly provide a wide range of functionalities for creating detailed plots. This section will provide a step-by-step guide to creating basic plots, integrating them into machine learning workflows, and interpreting the results. By leveraging these tools, we can generate visualization-driven insights that inform model development and optimization. Whether you're plotting cost functions or visualizing learning rate effects, Python's visualization capabilities are indispensable for understanding complex machine learning dynamics.
Visualization-driven insights have transformative potential in real-world machine learning applications. Through case studies, we can explore how visualizations have impacted model performance, identifying areas for improvement and optimization. These real-world examples illustrate the lessons learned from visualizing gradient descent processes, highlighting how insights gained have led to improved training methods. Visualization serves as a diagnostic tool, pinpointing issues and guiding corrective actions. By examining these case studies, we gain a deeper appreciation of the role visualization plays in enhancing model accuracy and efficiency, ultimately leading to more robust machine learning solutions.
As we conclude our exploration of visualizing gradient descent for better understanding, we have covered a range of visualization techniques that enhance our ability to interpret and optimize machine learning models. The importance of these visual tools cannot be overstated, as they provide clarity and insight that drive informed decision-making. We encourage you to apply the skills learned today, experimenting with different visualization methods to gain deeper insights into your models. For those eager to continue learning, numerous resources are available online to further your understanding. We invite you to engage with the community, sharing your experiences and discoveries. Thank you for joining us on this educational journey.